Imagine a road going between two things, a parking lot and a squirrel. This is the road here. Okay, the badger is going to travel along that road. So what he does is, first of all, he starts at his point of origin here, and he heads off to get his car from the garage. Off he goes. He goes to the garage, the car park, to get his car. Now that he's in his car, he goes along the road, past the squirrel, keeps going up the road, or maybe from the garage he reverses back away from the squirrel in the other direction. So how do we represent that line using vector notation in mathematics? Well, we use the letter R to represent where the badger is at any given time, R, and we start by describing using a vector the way that he gets to the garage. So off he goes. He's going along like this, and he goes to get his car. So in doing that, he creates this vector here. This vector here. And this vector gets him to the garage. Now, off he goes down the road. Towards the squirrel, past the squirrel, forwards like this. Maybe he goes one of whatever that distance is, one of them, or two of them, or three of them, or maybe he goes backwards. Maybe he does -1 of this movement here, -1 of them, and goes backwards down the road reversing. So what he's doing is he's going once he's got his car, he's going forward any amount he likes, and usually we use lambda to represent the number of times that he's gone forward. If we think of going forward a bit as being like from here to here, so this would be lambda is 1, lambda is 2, lambda is 1.5, lambda is -0.5, just represents how far he's gone really. And then the bit we're missing is how to represent mathematically that movement here. Well, that's a vector, and that vector, this one, can be thought of as the vector that gets you from the garage to the squirrel. So car to squirrel, that vector there is the vector that describes one movement, one direction. That's the direction of the line. So the blue one gets you to the line, and then once you're on the line, you do any amount you like of the direction of the line, and the direction of the line in this case is represented by car park to squirrel. And if you've watched the previous video, you know that car park to squirrel would be squirrel minus car park. As you can see, I've gone into proper hardcore maths here. Now let's say we're looking at the same road. We want the road to be the same, but I'm going to move the car park a little bit. So the car park can move down there, and the squirrel's going to go really close to the car park now, like that. Now obviously it's the same road, so the vector equation of this line should be the same. But what's changed in terms of the equation that we set up before? Well, we had R equals something plus lambda something. And in the first one we put how to get to the car. That's obviously changed. And in the second one we put what the direction of the road was, which was car park to squirrel. And that's obviously changed as well in a certain way. Now let's have a look at what the differences are. Before, the badger getting to the car was like this vector here, but now it's changed. Now it's doing this. It doesn't really matter. The road is still the same road, isn't it? So getting to the car is just getting to the road in a way. It doesn't matter where on the road the car park is. So instead of getting to car, I'm going to call it getting to the line. Doesn't matter how you get there, the line is just the line. Then car to squirrel. Now before, car to squirrel looked like this, and now car to squirrel looks like this. So what's the difference? Well, it's smaller and it's moved a bit further down the road, but we know from vectors that it doesn't matter where they are. This green vector here, for example, is the same wherever I put it, and it represents the direction of the road. So the fact that before I had the quite a long direction vector, now I've got quite a small direction vector, that doesn't matter. It's still describing that direction, which is if you go across this much, you go up this much, or if you go across this much, you go up this much, or if you go across this much, you go up this much. It describes the direction. So this bit here, car to squirrel, is the direction of the line. And you can find it if you know 2 points on the line, for example, the car park and the squirrel, by doing car park to squirrel, which is squirrel minus car park. But if you double it, it will still be the direction of the line. If you halve it, it will still be the direction of the line. Let's have a go at this question. So we're going to think of A as being where the car is parked, and we're going to think of B as being the squirrel. We know that the vector to get from the origin, that's the start point, to A, origin, bad writing, sorry. We know that this vector is 1, 3, minus 2, and we know that this vector is 2, 7, 0. Now it doesn't really matter which one's the parking lot and which one's the squirrel, to be honest. I'm going to think of A as being the parking lot and B as being the squirrel, but if you want to do it the other way around, that's absolutely fine. So the beginnings of my equation are going to look like this. First I go to get my car, 1, 3, minus 2. Then once I'm in my car, I can do any amount I like of the direction vector, and in this case the direction of the line is represented by the vector A to B, which is B minus A, which is 2, 7, 0, minus 1, 3, minus 2, which is 1, 4, 2. So that, 1, 4, 2, is the direction of the line, and there's my equation of a line, all done. Here's a fun problem. We've got a line, and we're told that the way to get to the line, or we're sort of told how to get to the line. We're told that if we do 1p minus 1, that's how we're going to get to where the car's parked. And then if we go off at 2, 1, 1, you can do as many of them as you like, you'll stay on the line. So here's the squirrel here. And we're asked to find out what p is. Now we're told this piece of information. 9, 7, 3 lies on the line. So somehow, by doing 9, 7, 3, I end up on the line. 9, 7, 3 is going to get me to the line. But I can get to that 973 by going via the car park, getting my car, and then doing some of these. So the question is, how many would I have to have done to get there? Well, let's make a little equation and find out. We know that 973 must equal 1p minus 1 plus an amount of 211, because it's on the line, and anything on the line can be written this way. So let's split that into the top, middle and bottom. 9 is 1 plus 2 lambda, 7 is p plus lambda, and 3 is minus 1 plus lambda. Now let's try and solve these. What does this one give us for lambda? It gives us lambda as 4. What about this one? What does that give us for lambda? Oh, that gives us lambda as 4 as well. I think we found out what lambda is. If we know what lambda is, can we find out what p is? Yes, we can. It's 3.